So today I'm going to talk about a few ways to improve your workflow. And I struggled a little bit with this title because these are ways to improve your work in general. And a lot of them are really suggestions for understanding features that you might not be aware that we offer. Um, so this is definitely not a FAQ. Um, we have a lot of documentation. Uh, the documentation is on docs.computecanada.ca for the most part. Is documentation available in some other places. Um, Almost everything I'm going to talk about is covered to some extent in the Docs wiki. One issue with the Docs wiki is that it's so big, it makes it a little bit hard to really get into. Um, we're thinking about making alternative ways to approach this, maybe domain specific. Um, anyway, this is in some ways derived from everything in the Docs wiki. One of the most important things, which I think is relevant to improving your workflow, is how you get support. Um, it's valuable if you do certain things that help us help you more efficiently. Um, Often people will open support tickets, which is the right thing to do, but they'll tell us something about, my program died, and then maybe they'll provide a screenshot or something like that. And that requires going back and forth between the support people and whoever opened the ticket just to get some basic information. So almost every ticket, you should always describe which cluster you're talking about, um, or which resource like a cloud. Please provide us with as much specifics as possible, things like job IDs and maybe even specific file names. Um, and when possible, please paste in relevant text like error messages rather than screenshots. And please don't put in videos unless your research is about videos or something like that. I guess I should also mention that there's an important feature of your account, which is that you can provide permission for support staff to look at your files. And I personally have mixed feelings about this because I don't like the fact that it's just sort of a single flag that lets support staff look at all your files. But in theory, that's not the way we use it. So we only look at your files when it's relevant to a ticket that you've opened. You can turn that off if you're not comfortable for that and give us explicit permission, perhaps when you open the ticket. But a lot of people find it efficient to allow us to look at your files. There are also many other sources of information. I mentioned the wiki. There's also training sessions, summer schools, intro seminars, the YouTube channels. Um, in some ways, you might want to open a ticket just to navigate all the sources of information. But again, on this slide, the main thing is try to give us the relevant information to specify, to pin down what your problem is. Um, Another very important thing that would help us is if people look at status.computecanada.ca. This is a website that we do a pretty good job of updating. When something's down, whether for planned or unplanned reasons, we'll update this status page. Um, we don't, we're not terribly rigorous in how often we update the status of a particular outage, for instance, but it's still the most reasonable first step. So if you're having trouble connecting to Cedar, for instance, it probably makes sense to look at the status page first to see whether this is a known issue with Cedar. This sounds like a very high level abstract comment about life cycle, but there's a reason that I mention it. So I'll go through the initial uh, comments, which are really about the structures of accounts. You get an account, all of that is documented on CCDB and the Docs wiki. Here are some things that might happen to you during your research life cycle. One is you may join another project. This gives you access to additional resources, may give you access to additional files. What happens here is that your account is given membership in another Unix group. Not really sure how to describe Unix groups if you've never experienced Unix before, but it's just a set of users who have certain properties. It's a grouping built into our identity infrastructure. Another thing that may happen to your account is you may change role. For instance, you may start out as an undergrad and become a grad student, and maybe grad student to faculty, and that's great. We track that as part of the account lifecycle. So when you do that, the phrase of art is a change of role. Your basic account doesn't change, and a lot of your files don't change, your login doesn't change, your password doesn't change, but you get access to a different set of groups. Changes of sponsor is a lot like joining another project, but it happens as well. One issue with changes of sponsor is that you may have to negotiate with both your old sponsor and your new sponsor about the ownership of your project files. Again, these are things where there's an offline component that may involve talking to sponsors or talking to us, and there's an online component that has to do with the ownership of the files. And generally speaking, it's not a matter of moving things around, but rather just relabeling the files. Here's one of my big take homes, and that is that every PI or project leader should establish sort of an agreement among sponsored users for how to handle the files. So it helps if at the very beginning, the PI has a policy. For instance, don't put any project files in your home directory. That's a very good policy. It's important to note that the way the file ownership works is that the file owner, which is the researcher, not the PI, we consider the files to be their private property. Even if it's in project space or nearline, it doesn't matter. It's the owner label on the file which determines what we can and can't do. That's even the case if the file exists in project space, which is technically owned by the sponsor. It's under their quota. So my suggestion is, at the beginning for every project, make sure that everyone is on board with this, but set group read and access bits for all project files. This will allow the PI and actually all group members to access files, and will simplify things when, for instance, a student leaves, because otherwise you have to contact us and we have to try to contact the student to get permission to change ownership of files. This is just a thing which, if you think about it at the beginning, will actually help you later on. Another important thing to do is to choose the right cluster. Now, each of the clusters has different resources. This should not be based on which region you're in. So for instance, if you're in the West, it isn't necessarily the case that Cedar is the right choice for you. And similarly, if you're at Guelph, it's not necessarily the case that Graham is the right cluster for you. The clusters each have somewhat different properties, and I've described them here. We can certainly help you choosing the right cluster, but really it's a question of what kind of jobs you think you're going to run. You should also try to use multiple clusters, so maybe there's no right cluster. If you use multiple clusters, you'll get a lot more work done. And the main problem with doing that is that you will probably have to move data around. So we don't have shared file systems that are shared between clusters. Eventually we may. It's hard to say about the future. Right now, each file system has its own storage, and they're not easily accessible between clusters either. So there are issues with moving data around. Different clusters have different models of resources. There are some smallish differences in things like scheduling policy. One of the valuable things that we're working on right now is data repositories. So if the files that you would have to be moving around are some sort of well-known data repository that you have cached for your own use, it may be that we can put those in a system managed repository. If it's like a NIH genetics database or a training data set for AI. Another thing that may be useful is containers. I'll mention them later on if we get to that slide. But containers are basically bundles of files, and the value of them is just that they ensure that your libraries and potentially data dependencies are bundled together into a single unit that you can move between clusters. One of the things that causes us the most enduring and persistent problems are small files. So all of our clusters have quotas for space usage. So in your home directory or your project or your Scratch, they also have quotas for file count. And the reason for that is just that it's very easy to run a bunch of jobs that each individually may access a same number of files. But if you happen to get enough resources to run 100 of them at once, you'll be accessing an insane number of files. So, OpenFOAM is notorious for generating very large numbers of outputs. And that may be fine at small scale, perhaps on your desktop, but it's not so great on our clusters. So it's really a question of trying not to generate large quantities of small files. There are lots of alternatives to large quantities of small files. If they're just sitting around, you can always use tar to bundle them. There are other tools as well. Zip is something in the Unix world as well. It may actually be very efficient to use a database. So our clusters provide database as a service, which is, I think, usually Postgres. And this allows you to make a connection to a local resource, which is very fast. And if your individual chunks of data are relatively small, meaning let's say under a megabyte or something like that, sticking them in an SQL database sounds strange, but it actually makes a lot more sense than making them files, especially if you have a lot of them. Consider using a smarter file format. This is a big problem for a lot of applications, which just want to write out large ASCII text files. Personally, I observe that programs have a life cycle where they start out being used sort of in a serial mode by a single person on a small computer and get jazzed up to run in parallel mode and on bigger data sets. And they wind up generating log files, which a human might have been able to read if you ran it on one core for 1 hour. But if you're running it on 500 cores for 10 days, the log files are just never going to be readable. So configuring your programs to generate less output is definitely a good idea. Ideally, we'd like all outputs to be binary rather than ASCII. And that's less convenient for things like post-processing, but it does mean that they'll be very compact. So HDF is a good example of something that stores binary data in a structured format. SquashFS is another tool that's less known. It allows you to create a read-only image, sort of like a tar file, but it's mountable and efficient to access and actually does compression internally. So, in cases where you might have, let's say, a large set of smallish genetic sequences that you want to keep separate, SquashFS will let you present something that is mountable as a file system, so they look like separate files, but it'll be very efficient. And the read-onliness might actually be of value in that case. And as I mentioned before, we're putting some effort into doing what we can to provide infrastructure for well-known data sets. Basically, if you think that there's a large data set which is causing you problems or you would like to use on our systems, please open a ticket and let us know about it. We know a lot about AI training data sets and genetics data sets. There are probably lots of other fields that have data sets which we could make available on the systems, so they wouldn't come out of your quota, and we'd make them available using consistent naming across all the systems. Another important thing is to realize that each job has an overhead. And there's a take home here, which isn't just to scold you for your short jobs, but there are important things you can do to improve the efficiency of your jobs just in terms of making them longer. So for instance, job arrays are a very attractive feature. Basically, job arrays allow you to do a single SBatch command that results in many jobs running. That's attractive. It doesn't address the 15-minute question. So job arrays are basically just a submission syntax that allows you to submit an item that sits in the scheduler. It's more efficient in the scheduler's queue, but it sort of generates a sequence of jobs, each with a different parameter. And that parameter is something that you can choose and use internally. My message here is that job array elements still have to be long. They shouldn't be short. And it could be that you should do that by bundling short jobs together. Another reason to bundle short jobs together is that we have a pretty strong bias in the scheduler for whole nodes. That is, if you just submit a serial job, of course, it's not a whole node job. It only takes a single core. If you submit an MPI job that uses, say, 32 cores, and you're thinking, oh, I happen to know that Graham, for instance, has 32 core nodes. If you submit an MPI job with 32 cores, it won't necessarily run, well, it won't run on a whole node. It'll actually run on 32 cores wherever the scheduler finds them. So whole node is very attractive for a lot of reasons. One is that it insulates you from noisy neighbors, that is, other people stealing resources from you. When you max out one kind of resource on a node, you should at least consider whether all the other resources will be valuable to you. So for instance, if you're using all 4 GPUs and the node has 4 GPUs, there's no reason to be parsimonious about your memory or CPU usage. It's something that you should probably test, but chances are you should allocate all the memory and all the CPUs. There are programs like Meta and GNU Parallel that let you set up basically a list of work units, like micro jobs, and it will run through them, execute them within the job context. So for instance, you can allocate a whole node and run Meta or GNU Parallel to run 10,000 work units, each of which runs for only a few minutes apiece. It's a way of bundling together smaller jobs. This is highly recommended on all of our systems. And in fact, on one of our systems, you can't even allocate less than a whole node. On the other hand, if you can't keep a whole node busy, don't allocate a whole node. I guess I want to think that goes without saying, but it doesn't really, because when you allocate a whole node, you'll be charged for the whole node resource. So that means that your fair share will be affected, and that may make your jobs wait longer in the future. Another curious suggestion is that there's a good time to use salloc and a good time to use SBatch. I'm a little surprised that a lot of people are using salloc on the login nodes and then doing what amounts to compute bound work within that context. And I think the reason for that is just that when you type salloc, you pretty promptly get something back. But the truth is that salloc and SBatch are doing practically the same thing. If you have something that's interactive, by all means, use interactive tools for that. There's a VDI system on Graham. There's Jupyter Hub on all the clusters now. You can do virtual desktops within Jupyter Hub. There's a lot of support for doing things interactively, but just consider, if you're typing Salic a lot, just consider whether you'd be better off with this batch. Another really important thing, which people sometimes think they should avoid, that it's just not worth doing, is to test your code for performance. So every program has a configuration of peak performance. And if you give it more resources than that peak, the performance of that application will actually go down. So for instance, you may have an MPI program and it may be tuned with your data set and our hardware. It may have a peak performance at 64 CPUs. That's a little bit small for an MPI application, but it's entirely possible. And if you don't test it for 96 and 128 CPUs, you might think that you're getting better performance, you're saving time, but you're using more resources, and that's going to hurt you in the long run. So the way to do this is really quite simple. You should probably start with a whole node, but within that whole node, your job script should run your program with 1 core, and then 2 cores, and then 4, 8, etc. The advantage of this is that you're getting the same resource, so you're comparing performance on the same resource. It's sort of an idealized scaling. And you can do the same thing across multiple nodes as well. But don't do that until you understand the single node scaling. And if you find unexpected numbers or you're surprised by the results you get, by all means, open a ticket. We love to figure out why something behaves the way it does. And there may be important lessons. You might be IO bound, for instance. Another aspect is memory. And the thing we observe is that people often equate getting more memory to making something run faster. And I'm not really sure why that is, but here are some pointers on memory. Obviously, don't ask for too much. The more memory you ask for, the longer your job will wait. If you ask for a large amount of memory per core, you'll be forced onto a subset of nodes within the cluster that have what we call high memory. These are nodes with, I think, 512 to 3 terabytes of memory per node. And the threshold for that is 12 gigabytes per core on, well, between 12 and 16 gigabytes per core. So if you run a serial job that uses 11 gigabytes of core, it will run on base nodes on all the clusters. But if you ask for 20 gigabytes per core, it will run on high memory nodes on all the clusters. And the big difference is that there are very, very much fewer high memory nodes. So it's important to get the memory ask right. It is difficult to predict. So one of the first things people ask us when they come to our environment is, how do I predict how much memory my program is going to use? Or for that matter, how should I predict how long my program will run? Because you have to specify both of those. And if you try to use more time or space, your job will get killed. And the answer is just estimate. And if you can increase the amount of memory or the number of cores or the runtime limit until it'll actually complete your job, and then you have a good estimate. You can ask for modest amounts of additional memory, and that will speed your job up, but only fairly modest amounts. So if you ask for extra memory, the program itself won't use any extra memory. It won't make the program faster, but it will allow the program to cache file IO a little bit more. And this is not a huge effect, but it's important. If you, for instance, if you somehow figured out the exact minimal amount of memory your job would use and you ask for just that, it would actually run faster if you asked for a little more. And that's just because of the IO caching effect. Java is notorious for being very, for being tuned to desktops. So it tends to try to detect the amount of memory on a hardware node and then size its memory use based on that by default. There are settings which are described in the docs wiki where you can tell it how much memory to use. That needs to be significantly less than the amount of memory you've allocated to your job, because that is just the Java heap, and there are other things that Java needs to do, such as the code, for instance. Another thing that often comes up is that some workflows involve memory use spikes, where some phase of a program or a particular program will use a very large amount of memory, but the rest of the workflow or the rest of the phases don't use that much. And if that's the case, you might want to consider splitting it up into multiple jobs. The Slurm version that we're propagating to all the clusters now actually does support heterogeneous jobs. This has always been a sticking point. In general, with Slurm, you get a homogeneous set of node allocations. So what you ask for is split evenly across nodes. But there is a way to request, for instance, 8 nodes, well, eight ranks in MPI with 4 gigs per core and 1 rank with 16 gigs per core. You can do that. Slurm will allocate uneven distributions like that. Probably should open a ticket if you try this, because there have been problems in the past and it's a little tricky to get right. The file system is also an important thing. And I think probably the little secret that I'll give you here is not so much a secret, but these file systems have very different performance characteristics in addition to their other characteristics. So for instance, local scratch, that is the 4th line there, is per node on systems that have it, not all do. And it's a local SSD. So it's very fast and very low latency. And that's different from basically all the other file systems. They may be fast in aggregate, but their latency is always going to be significantly more than you might be expecting. And the reason that I have this slide here is just that when people start using our resources, they're often surprised how bad the I/O is, because they're used to running on, say, a laptop that has an NVMe SSD, which is very, very fast. And we basically don't match that even with local scratch. Our systems are set up to achieve very high performance in aggregate, but that's spread across thousands of nodes. So I guess one message is, if you think the I/O is slow, don't despair, talk to us about it. But here are some pointers. So, home is, well, I won't repeat these. These are actually described in the docs wiki as well. Besides local scratch, I think it's important to realize, always emphasize, that scratch itself, the /scratch file system, is really intended only for inter-job temporary files. Maybe within a job, that might be okay. But temporary files, you should not have anything there that you're going to keep for more than, let's say, a week or 2. So you're probably aware that Scratch expires. We find lots of people do all their work in Scratch just because the quota system is simpler. And then they spend a lot of time making up for the fact that we try to expire files in Scratch. That's just an abuse, really. We tend not to try to pick on people who are doing this, but it's much better if the file systems are used the way they're intended to use. And basically, project is the place that you should start with. I'll also mention Nearline. If you're running into space issues, Nearline is very good because it's very large. So if you've got a project that you stopped working on or is done, it might make a lot of sense to stick it on Nearline. In our wiki, you'll find some notes about tools to use for Nearline. Basically, it allows you to put a few very large files, like up to 5,000 very large files, onto what looks like a normal file system, but the files get rolled off to tape in an invisible way. So the only way you can tell whether it's on disk or on tape is when you access it. If it's on tape, it'll take a couple minutes to start up. Another important thing that people don't necessarily think about is how they arrange file permissions so that the right people can get access to the right files? This is a very common question. And really my suggestion is two main things. One is ACLs, access control lists, are permissions that you can attach to files and directories. You can do it recursively. You can use these with just the normal usernames and group names, but you can also ask us to create a sharing group for you. So for instance, if it would be convenient for you to have, let's say, a project divided into two sets of people or two use cases, you can ask us to create a sharing group, which is essentially a new name, which can be used for ACLs. And then we hand this over, the PI can do this, and we hand this over to the manager of the sharing group, and they can put in whoever they want. And then that sharing group becomes a group on the Unix file system that can be used as a target for the ACLs as well. And the advantage here is just that it's much more compact. So, maybe you have, let's say you just have a single project, a PI has a single project and a set of grad students, and you want to set up some files which are accessible only to subsets of grad students. A sharing group might very well be the right way to do that. If the numbers of users involved are small, then simply listing the users explicitly in the ACLs might be doable as well. But the sharing group is basically a way to do that a little bit more efficiently. Our wiki has a lot of information about moving files around, but the first place you should probably look is Globus. I personally find Globus kind of clunky, but I like command line stuff. Globus is GUI and app oriented, and it can extend to your desktop as well. It's also sort of fire and forget, so you set up a transfer with Globus and you don't have to wait for it to complete. The traditional Unix command line tools like SCP, SFTP, rsync, SSHFS, they're sort of a different way of looking at file operations. SSHFS in particular, I think, is really important for people to realize exists. So SSHFS works under Mac OS and Windows as well as Linux. And it allows you to sort of like graft a remote file system onto your local system. So the files will appear virtually and act just like local files, except they'll be noticeably slower. It's built on the SSH infrastructure, so it's very efficient. Well, it's not very efficient. It's very easy to use once you started to use SSH. And it's also highly secure. So there are little tricks you can do with SSHFS, like dedicated keys. You can hand out an SSHFS key, a key for SSH, that allows a person who's not in Compute Canada to mount a file system, for instance. There are lots of things you can do. If you're trying to do something tricky, it might make sense to open a ticket with us, and we can help you make sure you're doing it in a good way. The basic thing to be aware of when you're moving files around is that storage quotas on Project Nearline are group-based. So basically project-based. And that means that if you're moving between Scratch and project, for instance, bad things will probably happen to the group label, depending on which groups you're a member of and things like that. We've tried to set up the project file system as well as possible, but there are some very loud warnings in the docs wiki about this, because you can create files on the destination file system which wind up feeding into the wrong quota, and that will cause you problems immediately. So if you think you're out of quota and you don't think that should be the case, this is probably the first thing we'll check. You can check it yourself as well. Our compute nodes are generally not on the internet, and that may be surprising if you're coming from certain other environments, especially a campus environment. Um, there are lots of reasons for this, primarily security. It's something that actually does differ between the clusters a little bit, but what we're trying to do is provide safe access to the internet. We're not really trying to block anything. We don't have an agenda. So here are some things that we do actually provide support for explicitly. For licenses, we make exceptions. Basically, if you need to talk to some outside resource, you can open a ticket, provide us with the name or IP address of that outside resource, and preferably the ports that it's using. So for a license server, for instance, that uses a system called FlexLM, there will typically be 2 ports and one file name, or sorry, one host name. If you can give us all of that right when you open the ticket, it makes it much faster. So, providing the exceptions to the firewalls or tunnels, these are very straightforward things we can do immediately, as long as we have the right information. We can also run license managers for you. So we do this in several cases. It does involve interaction with staff whenever the license gets updated or changed. So there can be some ticket exchanges to make that happen. But it's an important thing to realize that if you don't know where to run a license, it doesn't have to run on your campus necessarily. You can run it on one of our license servers. You might be trying to get to the internet because you have a database-driven workflow. And in that case, probably our first suggestion, maybe our best suggestion, is to use database as a service. This is a local SQL server. I mentioned it earlier. These are actually very fast. And since they're local, they're low latency connections. This is a very good option if you have a database-driven workflow. Space, these database servers have quite a bit of space. It's probably not going to be a problem unless you're using it as basically a file system and storing data in it rather than, information about sequence matches or something like that. We provide proxies in some places. A lot of internet access can actually go through a proxy. We have generic NAT in some places. This is unfortunately an area that is subject to change. We're definitely improving in some ways. It's also important to say that if you have production loads in particular that are very internet oriented, maybe you should stay in the cloud. Cloud VMs have internet access, and that might be an appropriate place to run a workflow of certain sorts. In addition, if you set up something, well, I should just say, it's possible if we think that your IP address has an abusive traffic pattern that we might block the IP address. When this happens, you'll just be denied from connecting to our resources, and you should open a ticket and please provide us your IP address. Consider using containers. This used to be an unusual thing, but Docker is quite common. We don't use Docker though. Docker can't be used in a shared environment in any secure way. We have something called Aptainer, which used to be known as Singularity. Runs quite a lot like Docker. It's certainly a container environment. We may add Podman, which is sort of a new implementation of Docker. Really, it's compatible with Docker and doesn't have the security issues of Docker. The big advantage of using containers is reproducibility, but also portability. And by portability, I'm including in that the fact that you can put your dependencies in the container. So your, library module dependencies can all be in the container, potentially along with data sets. It makes a big container, but it may be an efficient way to do it. It's also important to realize that we do provide VMs to everyone. All you have to do is ask. If you're going to ask for significant VMs, you might have to do an annual request. But for very small asks, there's a RAS for VMs. That may be an important part of your workflow, either as a front end for your workflow or as a place to do certain types of jobs. I guess it's important to realize that in the cloud, persistent VMs are very overcommitted, but that's okay because they're running things like web servers for the most part. There are compute VMs which are not overcommitted, but if you're running a compute VM, you should ask yourself whether you should be running on a cluster. Compute nodes are never overcommitted. There are a lot of them. The response time for allocating a compute node is obviously much faster than for spinning up a new VM. So jobs and VMs are sort of comparable in a way. And there are certain special cases which we can help you with. And I guess that's about it.